Okay, great. And also just wanted to confirm whether recording is fine with you.
I understand.
Okay, great. So,
Maybe my internet, just a moment. Maybe my internet connectivity is not well. So sometimes if there is some problem, that just bear with me.
sure. So our next speaker is Dr. Gautam Kumar. Gautam is working as an assistant professor in the Department of Mathematics, Faculty of Science and Technology at IFHEI Hyderabad. And his research interest is in convection in porous media, hydrodynamic instabilities, electrohydrodynamics, and geophysical fluid dynamics. So he obtained his PhD in mathematics from IIT Hyderabad and masters in mathematics from IIT Bombay, and then he worked as a postdoctoral researcher at IIT Hyderabad and IIT Gandhinagar before he relocated to Hong Kong for a longer period of postdoc and came back to India and currently working at Hyderabad. So over to you, Gautam.
Thank you for the nice introduction. Good afternoon, everyone. And first of all, I would like to thank the Professor Vikas and Satyajit for inviting me for this talk. So the title of my talk is it is my PhD work, and the title is the linear and nonlinear thermosoluble instability and inclined porous layer. So here we are considering the double diffusive convection in the presence of the concentration-based internal heat source, where the porous medium is inclined to the horizontal with some inclination angle phi. So this work is jointly with my PhD supervisor P.L. Narayana and my collaborator Professor Kirti Chandra Sahu. So the motivation for this work came from the recent Besham, in which they have studied the onset of convection in an inclined porous layer, and they found that the transverse rolls become unstable up to a certain inclination angle, and they found that value is phi is equal to 31.49 degree. And later, this work was extended by recent Barletta, but with a different boundary condition where they have considered the constant heat flux boundary condition. And in that case also, they found the similar analogy where the transverse rows exits up to the certain inclination, which is phi is equal to 32.54 degree. So what we are doing in this work here, we have considered instead of monodiffusive convection, we consider double diffusive convection, and also we consider the concentration-based internal heat source in an inclined porous layer. The problem here we have considered infinite large porous medium, which is has an inclination from the horizontal at phi degree, with considering the boundary condition in this form. So it seems to be chaotic, but here we consider this boundary condition and the depth of this says the z equal to 0 at we have t is equal to t naught plus delta t, and at the upper boundary we have t naught t equal to t naught and c is equal to c naught. So the flow dynamics govern in the porous media by the continuity equations, and the momentum equation is governed by the momentum equation is the Darcy's law. So the red one is the inclination, and this is the black one. It represents the standard Darcy's law, where we considers the gravity acting downwards in z direction. The energy equations as given by this, where m is the ratio of the specific heat into the porous medium to the specific heat of the fluid, and here alpha T is the thermal diffusivity. The next parameter here, this is the QD is the some proportionality constant based on the concentration, and here by the non-dimensionalization we will get a concentration based internal heat source, and the convection diffusion equation in the double diffusion case is governed by this. Here psi is the porosity, this epsilon is the porosity, and alpha c is the solutal diffusivity. The density of the double diffusive convection is uh, given by this, where beta T and beta C are the thermal expansion coefficient and the solutal expansion coefficient, where temperature reduce the density and adding the concentration make the fluid to be more denser. Now, due to we consider some non-dimensionalization to look at the stability of this system. For that, by using we consider some non-dimensionalization, which gives us this governing system of equation where RAS and RAT are the non-dimensional parameters. Q is also a non-dimensional parameter, which is based on the concentration-based internal heat source, and Le represents the double diffusive phenomena, which is the ratio of thermal diffusivity to the solutal diffusivity. Here we have taken the epsilon dash to be 1, and the non-dimensional boundary condition are as follows. So now we are looking for the stability, linear stability analysis, linear and non-linear of the system where we consider we find the base state solution to which we are looking for the instability analysis, where we perturb those base state solution and then we linearize by neglecting the product of the small perturbations, and later we decompose those perturbations into the normal modes, and by using that we try to get the generalized eigenvalue for this system of equation. So now here we have considered the steady parallel fully developed flow. We obtain the UBZ. Here small b represents the base states. As you can see, when we consider the steady states, we always consider that u bar, the base state solution velocity, is 0. But here we have considered UBZ, which says that there is a mean zero mean flow in the x direction, but there is something in the z direction. And by using the steps in the linear instability analysis, we obtain the system of equation which governs the linear stability of this problem. And here these quantities are given as this, with the following boundary condition. The above system with the following boundary condition constitute an eigenvalue problem where sigma is a complex number which represents the growth of the normal modes here. And we know that when sigma of r is greater than 0, then these normal modes are going to be unstable, and when the real sigma is less than 0, then we will get the stability. But we are here interested more into the when real of sigma is 0, that will give us the marginal stability boundary condition, and we are going to find the marginal stability boundary for the linear case. Here, RATC, the critical value of thermal Rayleigh number, can be obtained by minimizing over wave numbers. And here we are using the Chebyshev-Tau spectral method, which is coupled with QZ algorithm. We are trying to get the critical value by using this method. And here we are interested the stability boundary means like linear, as we know that linear instability gives us information instability above a certain above a critical value of Rayleigh number. And the nonlinear stability analysis is a sufficient condition which gives us a critical value of Ra. Below that value, the system is always stable. But here we are comparing this linear and nonlinear stability analysis with respect to the region of subcritical instability, in which we don't know whether the system is going to be stable or unstable. For the nonlinear stability analysis, we define an energy functional, which is the thermal energy as well as the solutal energy. And for that, we just differentiate energy with respect to time to get the production and distribution term. And to solve this energy problem, we define a maximization problem in this form where H is the admissible space for these variables theta, phi, and u. Now, when we define the maximization problem 1 by RE, then we can use it to get this bound. Here, as you can see, when RE is greater than 1, then these perturbations energy is going to decay with respect to time. Then we can say that the system is non-linearly stable when RE is greater than 1. And when RE is less than 1, then in that case, this quantity is going to be positive. That means that all those perturbations are growing with time, then the system is nonlinearly unstable. Now, for the global nonlinear stability analysis, we have to prove that all perturbations must decay to 0. Now, for that, we have, by this energy method, we have proved that, we have shown that theta and phi are decaying to 0 with respect to time. But how about the U? So by using AMGM inequality, we can show that U also decaying to 0 as theta and phi are decaying to 0 with respect to time. Now, what happens when RE is equal to 1? We can't conclude anything when RE is equal to 1. So we consider that critical argument, and to get the analysis with respect to the R equal to 1, we try to solve this maximization problem 1 by RE, which gives us the Euler-Lagrangian equation where we use lambda to be a Lagrangian multipliers. And the same with the following boundary conditions, we again obtain a system of generalized eigenvalue problem where RAT is the eigenvalue instead of the sigma. And similarly, we try to find the critical value in the case of linear analysis, where we maximize over tau, where tau is the coupling parameter, which is positive quantity. And here I'm using the golden section search ratio method to get the maximization over tau. Here A is the wave number, overall wave number, and X is equal to 0 represents the longitudinal rolls and AY represents the transverse rolls. Here L stands for the longitudinal rolls and the T stands for the transverse rolls. Now, if you look at the effect of the non-dimensional parameter, like we have obtained LE, RAT, and RAS, and we have Q. Now, in the absence of the concentration-based internal heat source, we try to analyze the longitudinal and transverse modes separately in the presence of the concentration-based internal heat source and absence. Now, as you can see here, when Q is 0, as you can see, for the negative value of RAS means that the lower layer of the porous medium is less concentrated than the upper one. So in that case, but here inclination we have taken phi to be 30 degree, which is going to impact the stabilization of this system. You can see that RAT all constant, and this open symbols represents the linear instability analysis, and the filled blue symbol represents a nonlinear. As you can see, for RA negative, the linear and nonlinear theories are coinciding. That means we can say that the linear theory is sufficient to predict the onset of convection, but for the positive value of RAS, RAT is constant up to LE less than or equal to 5, but later when the thermal diffusion is much higher than the solutal one, then in that case it reduces the critical value of RAT, and by which we can say that the onset of convections happen quickly for the higher value of Lewis number in the case of the longitudinal. But if you look for the transverse case, as for the negative value of RAS, when LE less than 1 means that when the thermal diffusion is less than the solutal one, it reduces the critical value of RAT, So here, as you can see that the lower layer is less dense than the upper layer, then it will have an unstable stratification. And also here mass transfer is happening faster from the higher region to the lower concentration region. But as further LE increases means like thermal diffusion is much higher than the solution one. In that case, it increases the RAT. That means the onset of convection, it delays. But for the positive value of RAS, when we have uh, dense solute at the lower layer than the upper one, in that case, when thermal diffusion is less, it has a stabilizing effect, but later when thermal diffusion is more, it has a destabilizing effect. Now, as you can see that the presence of Q reduces the critical value of RAT in both the case of longitudinal and transverse mode. That means the presence of the concentration-based internal heat source reducing the onset of convection in the it is the onset of convection has happened quickly. Now, if I move to the effect of phi, which is our important parameter in this work, here the same panels A and B in the absence of the concentration-based internal heat source, and Q, C, and D in the presence of the concentration-based internal heat source. So as you can notice here, when the phi is increasing means inclination is increasing. In that case, when the concentration for the negative value of Rs means for the unstable stratification, it influence the stabilization. That means that RAT is increasing with the inclination angle. And similarly, for RAS positive, it follows the same trend, but in the case of the RAS positive, the critical value of RAT is much higher than the low. Things came into the transverse case where all these modes are the stationary modes, and but here when inclination angle is between 0 to 4 degree, up to you can see that kink 1, these is transverse modes are stationary, but when this inclination angle is between 4 to 5 point something, then these stationary transverse modes turns into the oscillatory, and then again it switches from oscillatory to the stationary. So which is in the contradiction to the monodiffusive convection, where we was just getting the only stationary modes, not oscillatory. And here also, after this inclination value, the transverse modes are stable. That means there is no instability after this certain value of the inclination in the absence of the concentration-based internal heat source. Similarly, in the presence of the concentration-based internal heat source reduces the RAT in both the cases of negative RAS and positive RAS. As you can see here, the linear and nonlinear theories are coinciding. So we can say that the linear theory is convection in the presence of the concentration-based internal heat source. Now, if you look at this graph D, where for the transverse case, where we have Q is equal to 2, there is no oscillatory modes, only stationary modes are present in this case. And the region of subcritical instability does not exist for a short value of inclination angle. Later, it widens as the inclination increases. Now, in this work, we found that both stationary and the oscillatory modes occur in contrast to the monodiffusive system, where the only preferred modes in Boson paper, they have done this. And also here we have obtained the threshold value for the inclination angle below which the transverse rolls exist is 30 degree, 30.7 for Q in the absence of the concentration based internal heat source, and 31.92 degree in the presence of the concentration based internal heat source. Thank you. And this is my talk, and I will end up with this concluding remarks.
Thank you, Gautam. Quick
Thank you.
questions
Yeah.
from audience.
Yeah. Yeah.
Thank you. Hello, sir. I want to ask a question.
Yeah, please,
Yeah.
Deepali, go ahead.
So thank you, sir, for the nice presentation. I just want to ask that in your model, you have considered the viscosity as a constant. So if we take viscosity to be dependent on the concentration, what modifications and what are the challenges it will be there in your model so that we can do for that?
So it's like if we have the concentration based viscosity, okay, I just still in mind. It will if we have the concentration based, then definitely there will be one more independent parameter which will influence this the stability of the system.
Sir,
And
can we repeat your problem? I mean, just it is possible to do for that if I take mu as a variable, not
it
just
is
constant.
possible. Few
Okay.
people who have done taking the viscosity as dependent on the temperature,
Okay.
and then they have studied the stability analysis. Similarly, we can do for the viscosity depend on the concentration. Maybe it will just I think the convection, it will just the onset of convection will got delay because of that parameter, because the viscosity is depends on the concentration. Means the new parameter will introduce, and that may affect. Yeah, definitely.
Okay, sir. Thank you, sir.
Did you get the answer?
Yes, sir.
Thank you. So any other quick question, possibly one? Otherwise, we'll stop and take the break.
Hello, sir. Uh, Hello.
Yes, please go ahead.
Sir, nice presentation. I have a question. Uh, if you are using energy method, there is always globally nonlinear stability, or any conditional stability is coming.
Conditional stability, it depends. It may come because in that case, conditional for the energy method, we always look for the global stability, not the conditional one. But sometimes it could be conditional because Stohan and Paine, they have done this kind of energy method where we have the conditional stability.
Okay. Thank you, sir.
Yeah.
So thank you, Gautam, once again, and let me thank all the three speakers, including Hendrik. And Hendrik just dropped me a message that he had to leave because of some other commitments. So I thank all the three speakers of the first session, and we'll have a break, sort of, which is supposed to be 15 minutes, but due to time now it's cut short into 10 minutes. So I will keep the call on, and if you want to discuss with any of the speakers because of time constraint, which we could not happen during the in between the talks, that's fine. I will stop recording and feel free to discuss whatever you want to discuss. Thank you.